Finishing up nomenclature, wanted to give a few more examples. Here's one. So remember, you have to find the longest parent chain. If you number, that helps. So this is a heptane with 7 carbons. And remember, in the last session, we have the names of common alkyl substituents, and this is a tert-butyl group. So the names of those substituents really need to be memorized. And so this is 4-tert-butyl or T-butyl heptane. So the T is an acceptable abbreviation for tert. 4-tert-butyl heptane. Find the longest most substituted chain if you have multiple substituents. So looking here, we've got a chain that appears to be 1, 2, 3, 4, 5, 6 if you just use the straight chain part of it. However, if you go along, so you can see 4, 5, 6, this 6 carbon chain is preferred because it has 2 substituents. So it's the longest, most substituted chain. Aside from the fact that we would have a very hard time coming up with a name for this as a substituent, as it's shown, because it doesn't fit into any of the ones we've seen before. So this is a hexane. It has substituents apparently at 4 and 5, but then you say to yourself, oh, I'm supposed to give those substituents lower numbers collectively. So better to name this, numbering it in this way. 1, 2, 3, 4, 5, 6. So it's a 2-bromo, 3-ethyl hexane, or N-hexane. That's my script N. Technically needs to go in there. 2-bromo, 3-hexane. 3-ethyl N-hexane. So you have to recognize this as an ethyl group, of course. Everything continues to build on previous work. So if you're falling behind, it gets increasingly harder. Next topic is cyclic compounds, or rings. How does a ring structure compare with a straight chain compound? Say we wanted to make a ring out of a 1, 2, 3, 4, 5, out of a pentane. In order to make the ring, because carbon can't have more than 4 bonds, we have to remove 2 hydrogens. If we remove 2 hydrogens, then we can form a bond between the 2 carbons here to make a ring. That ring will be a cyclopentane. So if that's that carbon right there, that's carbon 5, 4, 3, 2, 1, putting that carbon in. So I'm just showing the carbons on the ends. And then the final bond to make the cyclopentane ring. There's a term for what happens in this case. The removal of 2 hydrogens, like you saw here and here, leads to the molecule having what we call one unsaturation. A ring is an unsaturation. We call it an unsaturation. So if you talk, so the way you would use it in a sentence is, how many unsaturations does that molecule have? And if it's cyclopentane, you would say 1. There's another version of unsaturations, actually more common, in fact. So if you remove 2 hydrogens from a molecule like this, it frees up these two carbons to create, this one's unchanged, this one has one hydrogen, to create a double bond. And I know you've seen these kinds of compounds if you just page through your book. The book is full of them. This is called an alkene. It's actually the next unit of study in chapter 13. So double bonds are one unsaturation. I guess I should say one double bond is one unsaturation. Double bonds are unsaturations. Okay, more about rings. Oh, and incidentally, so when you hear about saturated and unsaturated fats, that's exactly what they're referring to, the double bonds being there or not being there in fats, in dietary fats. So rings, this would be a cyclopropane because it has 3 carbons, 1, 2, 3. 4 carbons, cyclobutane. Oops. So you just put the word cyclo in front. Cyclopentane we've seen. Cyclohexane. Cycloheptane. Etc. So if you build the models of these, you'll see that these have flexible conformations. Remember the word conformation. Not detaching, switching bonds around, but just flexing, twisting, spinning, all that kind of stuff. And I urge you strongly to build models of these to see that. So it leads to some interesting phenomena. If you look at this model, the red substituents, okay, so the gray is the cyclohexane ring in the middle. The red at the beginning were substituents pointed out to the sides, and the blue were substituents pointing more straight up and down. See that at the beginning? All the blues are straight up and down, and the reds are all pointing outward toward the equator, if you think of it that way. By flexing the bonds of the cyclohexane ring, the gray atoms, all of the reds and blues interchange. So depending on what's attached in those positions, the reds and the blues, the molecule will flex and do this sort of ring flipping until it reaches its lowest energy state. It's actually a pretty important concept in organic chemistry. The fact that conformations, molecules that are flexible, that can spin, twist, rotate, so forth, will settle into the lowest energy state. In doing so, the positions of the things attached to the ring, as you see here, can all switch around. But they're only moving in space. The bonds are not detaching. Groups are not changing what they're attached to. On the example on the right is cyclohexane, as we see it often drawn in 2 dimensions, basically. And let's say we have a CH3 group pointing up toward us and an OH group pointing away from us. Remember, I've introduced this way of drawing 3-dimensionality. The bottom is more like what you would see if you built a model of this. And this model might look like this. So not using wedge and hash marks, but this is more like a conformational representation. We'll call it a diagram. So we have lots of different ways to view molecules, depending on the problem we're faced with, how to analyze what's going on, for example, in a reaction. So this happens to be the more energetically preferred type of conformation that cyclohexane will flex into. You'll see that if you build the models, the molecule will sort of just, you can actually feel it ease into place. Finally, for chapter 12, we want to survey functional groups, and the emphasis right now will be on recognition of functional groups. So later we're going to explore the chemistry of each of the functional groups in detail, how they react and how they behave. Table 12.1 is a great summary of all the functional groups that we want to recognize. You can omit these two. So alkenes we have just seen above. So alkenes, carbon-carbon double bonds connected to whatever. That's my squiggly lines, connected to whatever. Alkynes are triple bonds. And these are linear molecules. So this is trigonal planar geometry. I know that was covered in Gen Chem, but we can take another look. Linear. And if you recall, alkanes, tetrahedral. So these are the geometries of the molecules. But importantly, we want to recognize double bonds and triple bonds as alkenes and alkyne compounds. Aromatics are kind of a special case of alkenes. So an aromatic benzene ring, this compound is called benzene, has multiple double bonds like this in a ring shape. You want to be able to recognize that benzene type ring as an aromatic ring. Alkyl halides, well, basically anything with a carbon that has halogen or halide on it. So fluorine, chlorine, bromine, iodine, X equals. So alkyl halides are functional groups. They behave in very particular ways. Now I lump these into categories that maybe will make them a little easier to remember. So alcohols, ethers, amines, and thiols, and you do need to know how to spell these. Okay, so all have single bonded oxygen, nitrogen, or sulfur in them. So I'm grouping them together. An alcohol, for example, has this look. So there's a carbon there, of course. So this is an alcohol. I'm going to talk a little bit more about those later. Ethers are oxygen connected to two other carbons. So that's an ether. And an amine is nitrogen connected to a carbon, which in turn is connected to whatever else. Amines need the nitrogen to have 3 bonds and a lone pair. So that's an amine. The 3 bonds actually can be all carbon. So this would equally be an amine with a lone pair there. Or it could be 2 carbons and a hydrogen. Thiols are the sulfur version of alcohols. That's how I remember it. And so they have the alls ending. And so sulfur attached to a carbon, whatever, with like hydrogen on it, like that. Looks like an OH group, only it's an SH. That's a thiol. And sulfides are the sulfur version of ethers. So this is why I put these all together in this group. Sulfur version of ether would be a sulfur connected to 2 other carbons and so on in the other directions. Incidentally, sulfur would have 2 lone pairs in both of these. And in the ethers, oxygen also 2 lone pairs. In the alcohols, 2 lone pairs. Worth pointing out. Then we have a group of carbon-oxygen double-bonded compounds. And so a carbon-oxygen double bond is called a carbonyl group. So there's a number of variations of this. Aldehydes are a carbonyl containing group connected to a carbon on one side and a hydrogen on the other. That's an aldehyde. A ketone is a carbonyl connected to carbons on both sides. A carboxylic acid is a carbonyl connected to an OH on one side and carbon, etc. on the other. An ester is a carbonyl connected to an oxygen, further connected to a carbonyl on one side, connected to a carbon, and to a carbon on the other side. And finally, an amide is the last one for now. Carbonyl group connected to a nitrogen, connected to a well, not necessarily connected to a carbon, connected to a carbon on this side. This nitrogen could be connected to C or H with its other 2 bonds. Could be both hydrogens, so this would be an amide, NH2. But really more commonly, amides would look like this. Nitrogen with 1 hydrogen on it and a carbon group most likely on the other side. So we want to be able to just simply recognize all these groups. There's one final note on alcohols. And we're going a little long here, but that's okay. So final note on alcohols. An alcohol connected to a carbon like this, that's connected to one other carbon, is a primary alcohol. And it looks like a 1 degree. And then an alcohol connected to a carbon that has 2 carbons attached to it. And so maybe 1 hydrogen there. Not maybe. That's a secondary alcohol. And in logical progression, a carbon that's connected to 3 other carbons with an alcohol on it, no hydrogens on that carbon, is a tertiary alcohol. So we want to be able to recognize those. So some memorization here. Here's an example of how we would apply this, for example. So here's a molecule called dynomycin. It was an anti-tumor drug that was being investigated. I'm going to identify the functional groups here. So this is an alcohol, right? This is a ketone. Here we have an amine. Here we have, going back to the beginning, alkyne. This is a carboxylic acid. And this is an ether. So look, it's an oxygen with 2 carbons on either side, an ether. Ether and ester sound the same, but they look totally different. So final note, functional groups are identified as exact units. So if you have something that looks like this, you cannot call this an ester, and you cannot call this a ketone, and you can't refer to this as an ester next to a ketone. Because they're all connected as one unit, essentially, this is called an anhydride, which was one of the ones I told you to ignore for now. But it makes for a good example. You can't pick these apart and say ketone, ketone ether, or ester ketone, or anything like that. So these functional groups exist as discrete entities and are recognized that way. So, you know, among the more common errors are like someone calling this an amine and this a ketone. That's not the case. This is an amide. Okay, so recognition of functional groups. And that's the last video for this unit. So a little bit longer, but that's the last one.